right, hi everybody. So now we're going to take a look at limits. Okay, and specifically right now in the introduction here, we're going to take a look at something called the limit of a function. What we're addressing here is essentially this question right here. What happens, okay, to the values of f of x? Okay, let's say y equals f of x as x gets closer and closer to a specific value, and again at this point here, maybe it's not important here, let's just call it a. So what happens to the values of y equals f of x as x gets closer and closer to a specific value a? Now this is kind of a predictive thing. Okay, I guess this is in a sense here a little bit predictive here, because what we're trying to do is we're trying to anticipate what the value of the y coordinate is as the x coordinate gets closer and closer to a specific value. Okay, and I will talk a little bit more about that. I'm going to draw this out a little bit and you'll see it in a bit here. The reason why this is important, and this is probably going to be one of those things in this course, okay, in a calculus course, getting your head wrapped around what a limit is going to be one of those more difficult things. But once you got it, once you you clamp on to what this idea is, the rest of calculus kind of falls out nicely from this. In fact, way back then, when calculus was first on the scene, when Newton was working on it, he did not use limits, the idea of a limit. This came a fair bit after him. He used something called infinitesimals. Okay, and there were these little objects here, these little symbols that look like little sigmas, I believe is what he used. I might be wrong with that, but anyway, he used these things called infinitesimals, and the purpose of that was basically to handle the absence of this concept of a limit. And what infinitesimals were is they were numbers that were essentially zero, but they weren't zero. But they were so small they acted like zero, but we got to state they weren't equal to zero. It was just really confusing. And even when Newton was confronted, when he was asked to explain his reasoning with these things called infinitesimals, even he wasn't quite sure what to say about it, other than the fact that, hey, it works. The math that I'm doing here works. Now, it was quite a while afterwards that we come up with this idea of a limit. Okay, and we got to explain how this works here. Now, it's written like this. Okay, so what I just explained right here would be written like this. Lim, okay, and then we put x with a little arrow, and then the letter a, and this is underneath, there's small little values underneath here. Okay, so it's not like one line and the next line. This is like one line and then this is little small script underneath. And this would be f of x. So this is the limit of f of x as x approaches a is going to equal some L for limit. Okay, so the limit of a function as x approaches a is equal to L here. So again, what we're trying to do here is we're trying to predict the behavior of the function as x approaches some value of a here. Now, for right now, just so that you don't get overly lost in this, because there is a very solid idea here, and it's actually quite straightforward for the most part. Let's just take a look, for example, at the line y equals, and let's call this f of x, and let's just make this something simple like x plus 1. Okay, just really straightforward little function here, and let's graph it to start off with. Okay, and so x plus 1 right there. So x plus 1, my graph's going to look something like this. Now, and let's just say that what we were asked to determine here is I'm asking, what is the limit as x approaches, let's say, 1 of f of x? Okay, I'm going to call that L. I'm going to figure out what L here is in a second here. Now, I'm going to state this, I'm going to try to state this as simply as I can, and then in a few minutes here I'm going to look at a much more involved definition. But right now, just so that you catch the idea here, what I'm saying is that as my x coordinate, okay, as my x coordinate approaches 1, So here's the x value of 1. Okay, I'm going to, what I'm going to do is I'm going to use this pencil right here to point to the point on the line as I do this. So as my x coordinate here approaches 1, what is happening to the y coordinate? Or even maybe better yet, maybe what I should be doing is pointing just at the y coordinate. So as this point, the x value moves over, and I'm pointing to different points on the x-axis here, what y coordinate is this pencil moving towards? And I hope you can see that here. As the x value approaches 1, the point that I'm drawing out here is approaching a y coordinate of 2. So in this case here, this would equal 2. So the limit as x approaches 1 of f of x is going to equal 2. Now, that worked out nicely here because of some properties of this linear function that I'm working with that basically make it really easy to work with when I apply limits. Okay, but that should give you kind of the basic idea. That's all we're asking here is, now I'm not, and this is the weird part here, I am not technically asking what does the function equal when x is equal to 1. Okay, this is something different. Okay, this is not f of 1 equals 2, although that's true. When I ask what the limit is as x approaches 1, this is not strictly true. I'm not asking what that's equal to. However, they are very, very closely linked ideas. And so you might end up using this to figure this out. Okay? And you'll see in a little bit here why this is not exactly what I'm asking here. However, it's so closely related that, yeah, we'll often do this to get that answer. Again, what I'm asking for here is just what am I approaching? I'm predicting. I'm saying here that I am predicting that as x gets closer to 1, the y coordinates are getting closer to 2. Okay? I do not, as I slide along here, I don't actually get to 1. I'm never saying that I actually arrive at x equal to 1, which means I never actually arrive at y equals 2, I should say. But that's where we're headed here. Okay, so that's the idea. And you will see in a little bit why this is so important in calculus. This is kind of that fundamental idea. This is the springboard into the idea that makes calculus really, really work. Now, what I'm going to do here is I'm going to throw a couple definitions on here of limits, and we're going to explore this a little bit, but not much. Okay? And you'll see why in a second here. Now, I suspect that after I throw down my two definitions here, I am likely to generate a little bit of frustration out there. Okay? But I'm going to give you guys both the heuristic definition of a limit and what we call the formal definition of a limit. I'm giving these to you here. I'm kind of in a bit of a catch-22 here. High school calculus, we are not going to use these two definitions that I'm about to give you. We're not. That's not ultimately the goal of high school calculus. However, having said that, the goal of high school calculus is to set the stage for university calculus. And really, that's how you want to think about a calculus class in high school. It really is like a pre-calculus class. When you go to university, you're going to quickly run over a lot of this material that we do in this course again. Okay, so all we're really doing here is getting your motor running, pointing you in the right direction, and then letting you go here. So having said that, I want to give you a couple of the definitions here that you might encounter at a university level. I will try to explain very quickly how they work, because when I first write these down, they are not going to make a lot of sense. I'm going to try to explain it to you, draw it out for you. But don't worry too much if you get lost in the definition. I'm really throwing this down so that you'll see it again and you'll maybe recognize it, and the more you see it, the more you hear it, it'll kind of click in what's going on. So here we go. So L is the limit, okay, of f of x as x approaches a if for any, now here we go, positive tolerance, okay, any positive tolerance, epsilon greater than 0. Now, okay, it's going to be easy to get a little bit lost in this, but what I'm saying here is any positive tolerance. Now, if you think to your physics, chemistry, whatever, any science there, when we start talking about tolerance here, what I'm saying here is that there's a kind of a plus or minus. There's a goal that I'm shooting for, some value that I'm shooting for, but I'm okay if I'm within some sort of range, some interval around that target number here. That's my tolerance here. So, and I'm going to call that tolerance epsilon, and it's going to be positive. Basically, I mean, it doesn't make sense to talk about negative tolerance. That makes no sense. So perhaps it's redundant to throw the word positive in there. However, we're covering our butts here. So for any positive tolerance, epsilon greater than 0, we can ensure that f of x approximates L. Okay, remember, L is supposed to be our limit. Okay, really what we're going to do with this definition is kind of like verifying that L is in fact the limit. We guessed that L was the limit, now we're going to verify that it is the limit. We can ensure that f of x approximates L with error less than epsilon, which is what we want. That's my tolerance, right? So I certainly don't want to miss my target by more than epsilon. Epsilon is what I'm allowed. Epsilon at any x other than possibly A itself. And that's kind of a bizarre little statement there. And in fact, when I was in your position learning this, I was okay with this until like that line right there. That I was like, oh, now what are you talking about here? I almost need to draw the diagram to explain what's going on here. So other than possibly A itself, provided x is close enough to A. Okay, that is what we call the heuristic definition. It's kind of a rule of thumb definition. Now that doesn't, if you've never really been exposed to this kind of mathematical terminology before and explaining it like that, that's probably not going to seem like it's all that helpful. Well, let me show you another one here. And then what we'll do is I'll diagram it out for you. And then what we'll do is we'll back off a little bit. I want you to see this. I'm going to throw it to you up front early, get it over with, and then we're going to move on and do some stuff that's a little bit more useful. Now we're going to take a look at the formal definition. This is going to be even more mathy. Okay? The formal definition looks more like this. We say L is the limit of f of x as x approaches A. Okay, so if for every epsilon greater than 0, so we're back to that tolerance. Okay, so I'm allowing for a little bit of give and take on either side of my target value. If for every epsilon greater than 0, there exists a delta greater than 0, oh boy, such that if, okay, now here we go. So if the absolute value of x minus A is less than delta, then the absolute value of f of x minus L is less than epsilon. Then we say, okay, the limit as x approaches A of f of x is equal to L. Okay, now that probably doesn't make a whole lot of sense. Probably neither does the heuristic definition there, okay? However, I have found that once you take a look at the diagram, that actually it's not that confusing, okay? It actually makes a lot more sense here. So I'll show you the diagram in just a second. Okay, so let's have a look at what that formal definition is actually saying about a limit. So here's our function, okay, f of x. Now, let's say that we are interested in what the limit of the function here is as x approaches a. Now we look up here and we're going to guess that it's this point right here. Okay, so it's this guy right here is what we're looking at here. Now, there may be an open dot there may be a closed dot there. The function might exist there, it might not exist there. If you go back to the definition, you'll notice that it's the one line in there said, except possibly at a. I don't really care what the function is at a. If you look back at the formal definition, you'll notice that when we found the interval, when we did x is minus a, we said it was greater than 0. Okay, so we're not interested in x being equal to a. I don't care. I don't care what actually happens at a. Now that's kind of a weird concept. I don't care. I am taking the limit as x approaches a, but I don't care what happens at a. Now here's how this works. We're going to introduce, an epsilon here. Now first of all, I'm going to come straight across here. Here's my L. This is what I anticipate the limit being. And I think that stands to reason. As I approach x, okay, as I point to the point along the curve here and just let the x coordinates get closer and closer to a, I am assuming that I'm going to get closer and closer, the y coordinates get closer and closer to this L here. Now I am going to create a tolerance. Okay, I'm going to offer some epsilon, positive epsilon, greater than 0, okay, positive epsilon, and I'm going to use that as a tolerance here. So that's going to give me a boundary here. So I'm going to write this out here with a highlighter so that you can see this. So I'm going to draw that line right there, and then I'm going to draw this line right here. Now, here's my L coming across right here. That's exactly the value L here. Let's assume that this distance right here, this distance right here, this is my epsilon, that's my epsilon. So the top, okay, this is going to be L plus epsilon. My bottom here is going to be L minus epsilon. So what I want to do here to verify that L, okay, to verify that L is the limit of this function as x approaches a, first of all, I'm going to choose a tolerance. So I'm going to say I will be happy so long as I can get to close enough to L to be within this here. Now, what the formal definition of that limit says here, that if you throw down an epsilon, if you pick an epsilon like this, that what that does is that creates for me a delta. We're saying that these two boundary lines here essentially create for me boundaries for x, and I'll show you how that works here. Now this isn't exactly the way this has to work here, but I think this provides a really good visual of this. If you look at where my L plus epsilon goes, I hit here. What's that x value? Well, I don't know. It's going to be a little bit smaller than a. If I go to where my low end of my interval hits my graph, go down, it gives me that high value of a here. So we call this separation right here, from there to there, there to there, this is my delta. So this right here, this is going to be a minus delta. This is going to be over here, this is going to be a plus delta. Now, the way this works here, the way the definition works here, it says that as soon as you choose, okay, as soon as you choose an epsilon, okay, as soon as you choose an epsilon, does that therefore create an interval here that's basically 2 delta wide around A, such that if I'm inside that interval, it forces me to be inside this interval. So if I choose an x value inside the interval from A minus delta to A plus delta, if I choose there, am I necessarily in the interval between L minus epsilon and L plus epsilon? In this case, yes, I am. Now, what's really important about this, and it's something we haven't emphasized at this point, is that the size of epsilon is arbitrary. Okay? It can be as large or as small as I want. So what I do now is I say, well, sure, it works here. If I draw that line right there, I get get this interval right here. But what if I make my epsilon smaller? So let's go across here. Let's just use this pink highlighter. And let's create a smaller interval along the y-axis here. So here's my even smaller. This is now my epsilon 1. Ooh, itty bitty epsilon 1. Okay, so now this top here is going to be L plus epsilon 1. This is going to be L minus epsilon 1. And when I do that, that creates a brand new interval right here. That narrows this up a little bit. Okay, so now all of a sudden I've created this new delta, and maybe I'll erase this down here. Just kind of do this again because I want this to be as clear as possible. This creates a new interval, and now I've got these new deltas here. So this is going to be, this right here is going to be A minus delta 1. This right here will be A plus delta 1. Now, I imposed a brand new epsilon on there. That has created for me a new delta. Now, is it true that if I pick an x value within this new interval right there, do I automatically get within the new interval here around L? And again, the answer is yes. So if that's true, if it doesn't matter how small I make that, if no matter how small I make this little band around my L, does it always create a little band here around A, so that if I was inside this little interval around A, I'm automatically inside this interval around L? If that's true, then therefore L is the limit as x approaches A of f of x. And that's what we mean by that. I think the diagram helps a lot here. So if I create this little interval here, make it smaller, basically it's hard to do this. I zoom in on here. Does zooming in this way cause me to zoom in this way? Does zooming in on L vertically cause me to zoom in on A horizontally? And if the answer is yes, then that value that I picked there, L, is in fact the limit of the function. All right, now just a few remarks about what we've just looked at. First of all, number one, for the limit as x approaches A of f of x to exist, okay, so even just to start that sentence here, obviously the existence of a limit is an issue, okay? Whether or not it's even possible to do what we're about to do here, certain things have to be in place here. So for the limit of f of, as x approaches A of f of x to exist, f of x, okay, must be defined on the open interval, okay, and we'll use just alpha and let's say beta, open interval alpha to beta, containing x equals A, except possibly, and this is going to be part of our next comment here, except possibly x equals A. Now, what we mean by this is being strict to the definition, the formal definition of a limit here. When we go back up here, we're talking about the interval around the A, okay? There has to be this open interval around A that I can get inside. Now, and that's why it has to be an open interval. It can't be a closed interval here. Because there always has to be this. As soon as you close the interval, you end up creating a possibility where this isn't quite true here. But as long as it's an open interval, I can get as close as I want to A without getting to the end of this. Okay, there's always going to be a value inside there. I know that seems a little bit goofy, but trust me on this one for right now. There has to be some interval around A that I can get into now, but from either direction. Okay. This open interval, A is on the inside, and the fact that it's got to be open on both sides, I have to be able to approach it from both sides, that is significant. Okay, so in order for the limit to exist, there's got to be this interval around A. I need to be able to draw this a little line, like if I pull out the highlighter, I need to highlight a little region of the x-axis around A, over top of A, but on both sides, and then I'm okay there. Second comment that we might make here. The value, okay, of f of a, if it is defined at all, sorry, I'll write that over here, if it is defined at all, does not affect the existence of the limit or its value. Now again, the reason for this is because what I'm doing here, if I go back to my diagram, I am saying that as I vertically zoom in on that L, I'm asking, does it cause the interval around A to kind of zoom in on A? Now, and I'm always using an open interval, so there's always a little bit of room on either side of A, which gives me a little bit of room on either side of L. I never actually get to the value x equals A. Okay, I never do. It's an open interval. There's always this little bit of wiggle in there. Okay, so what that means is I don't even care if the function is it does exist here. In fact, that function, that might be an open hole, and that hole might even be defined, or it might be defined up there. I don't care. I don't care at all what actually happens at x equals A. I only care what happens in that little interval around A, which is related to that little bit of an interval around L. So that's what this second comment is all about. This third comment is what we're going to explore, and we're going to do a lot of work with in the next lesson or two here. If two functions are equal, except possibly at A, it's always that, there's always that little exception at x equals A, except possibly at x equals A, then their limiting behavior at A is the same. Now, we are looking at two functions that are basically equal, except for well, I could say it could be an infinite number of points, quite honestly, but they're equal over real intervals, several real intervals. So if they're not equal, basically what we're meaning is that they're not equal at discrete points, not over intervals. So there might be a whole bunch of, there might be a whole bunch of open circles here. Open circle, open circle, open circle, open circle, all along this line here. But that's interspersed with a whole bunch of real intervals. They might be small, but they still exist. Okay, where I'm drawing the line, drawing the line, drawing the line here. As long as that's true, okay, then those two functions, if they're same as each other, basically, except they don't exist, they're not the same at those discrete points, then their limiting behavior is going to be the same. So again, I might have this line and it might be a smooth line. I draw it all the way through here, but then the next one's got a whole bunch of little holes in it. The limiting behavior all along those two curves are going to be exactly the same, because it doesn't matter what happens at a specific number. Okay, it only matters what happens in an interval. That's why even if I've got a bunch of these little holes in there, these specific numbers that don't exist there on one function, it will behave, in terms of limiting behavior, it will behave the same as that smooth curve. Okay. Now we'll take a look at a couple of examples here. At least I'll show you how this works. Again, this is going to be a little bit awkward to start off with, and that's okay. That's okay. You kind of got to grin and bear it. One of these. Well, I'll say that differently. As you go through calculus here, this first chapter here on limits, where we really start to get into this more calculus kind of idea, this is a hard idea to get your head around. Sometimes you just kind of got to grin and bear it, and when you get beyond limits, it gets a lot easier to work with. Okay, now let's take a look at an example here. So let's take a look at the question that says that we're looking for the limit as x approaches 4 of 2x minus 5. Okay, and what we're going to do here is I'm going to say right now that this is going to equal 3. Okay, we're going to guess that that is equal to 3. What we're going to do is I'm going to show you how you can verify that. Okay. Now, on the face of it, you might say, well, yeah, that I would think so, because if you plug the 4 in, 2 times 4 is 8, minus 5 is equal to 3. And that's actually not a bad argument, because in most cases, what the value that a function approaches, okay, is what the function is going to equal at that point here. But that's not always true. And what I want to do to start off with here is, though, I want to show you how that epsilon delta proof or verification works here, how the definition here works. So again, we're going to check here that the limit as x approaches 4 of 2x minus 5, we're going to verify that that is actually equal to 3 here. Now, the way we do that is we're going to take a look at our epsilon delta definition here. So remember what that says here. It says that if you've got some sort of epsilon that you're working with, okay, and so what we're going to do here is we're going to get the difference between our function and our limit here, L, to try to get that within epsilon here. So we're going to assume that that's true. So here's our function, 2x minus 5, and then we're going to subtract the 3 from that. So the difference between our function and what we think the limit should be, we're going to assume that we can get that to within epsilon. Now, if that's true, we should be able to see that forcing some sort of relationship here with x, okay, and delta here. And I'll show you how that works in just a second here. So we can simplify this a little bit. So this is our remember, this is our f of x minus L. That goes back to our definition. We're going to state that it's less than some sort of epsilon here. At this point, I haven't even suggested what that is. What I need to show here is I need to be able to take this relationship and show that it implies a relationship between x and, quite honestly, that 4 right there. And I'll show you how that works. In this case right here, we're going to get 2x, and negative 5 minus 3 is going to be negative 8. Okay, that's still going to be less than epsilon here. Notice that you can factor out a 2 out of that. So this is going to be 2 multiplied by x minus 4. That's all still in absolute values. It's less than epsilon. Now, that's a positive 2 that I pulled out, and it's within the absolute values. I can actually factor that out. Okay, pull that right out. And then I can divide both sides by that 2. And I get epsilon over 2. Now, look at what just happened there. Actually, maybe we'll do a zoom in. Whoops, we'll zoom in a little bit. Notice what just happened here. I went from f of x minus L was less than some epsilon. And by just simplifying that and pulling out that 2, what I've got now is I've got x minus 4. This is x minus a, and I've shown that this is less than epsilon over 2. So that delta that we were looking for is going to be equal to epsilon over 2. So in this particular case here, for whatever epsilon that I choose, I can get the delta that I need simply by dividing that epsilon by 2. That's what allows me to conclude that, yeah, that 3 is the limit. That works. That is how that definition works. Okay? I'm assuming that some epsilon exists, and by assuming that that exists up here, I am able to systematically work my way down with that given information to the point where I get the x minus the value that it's approaching, and I get some sort of relationship here with epsilon. And that relationship right there is now we're going to be represented by my delta. Okay? Now, I don't want to do a lot of examples like that. In fact, this is really the only one that I want to take a look at. Only because this is not something that we're going to get to a lot in high school. For the most part, our limits that we're going to approach are not going to be this complicated. However, I do want to go back to this. I want to take a look at it in a slightly different way here. So we're going to take a look at the limit as x approaches 4, again of 2x minus 5. Now, maybe I don't know what the answer is to this. Okay, one of the things that I want you to know about this is I want to go back to that remark that we made a little while ago here, and about being able to approach it on an open interval. Okay, in order for a limit to exist, okay, say, so to exist, I must be able to approach, okay, now in this case, I must be able to approach the 4 from both sides. Now let's just take a look at what happens when I do that. So I'm going to put my x coordinate here. I'm going to build a little table of values actually. I'm going to have 2x minus 5. And what we'll do to start off with here is I'm going to quite literally approach 4, but I'm going to approach it from the left-hand side. Okay, I'm going to approach it from the left. Now, the notation that we typically use is we're going to take the limit as x approaches 4, and then what I do is I put a little negative sign up front here, or up top there in this superscript. And that little negative there means I'm approaching it from the negative side of 4, towards the negative values on the number line. And if I plug 3.9 into that and evaluate it, I will get 2.8. Now let's get a little bit closer. Let's make it 3.99. When you plug that in, you will get 2.98. Let's get even closer, 3.999. When I do that, I get 2.998. Let's get even closer, 3.9999. And when I do that, I get 2.9998. Now look what number this is approaching. Can you anticipate where that's going here? As this gets closer and closer to 4, this number here is getting closer and closer to 3. Awesome. So when I approach the 4 from the left, I'm getting 3. Now, let's do this again. 2x minus 5. But this time, let's approach it from the right-hand side. So I'm going to put a 4.1 in there. And now you can probably guess at this point what that notation looks like. We're going to approach 4. I'm going to put a little subscript positive sign up there. 2x minus 5. Figure out what that equals in a second here. When I plug 4.1 into that, as a result, I get 3.2. If I plug in 4.01, I get 3.02. Okay. If I plug in 1, I get 3.002. 4.0001, I get 3.0002. And again, you can see the closer I get to 4, the closer these values here are getting to 3. And so I might say that as I approach 4 from the right, okay, the limit is going to be 3. Now, because these two are the same, okay, because approaching it from the left and approaching it from the right yield the same value, I can conclude over here, okay, that therefore the limit as x approaches 4 for 2x minus 5 is going to equal 3. Okay. Now, it is not an insignificant thing to notice that in this particular case here, when I wanted to find the limit as x approaches 4 for 2x minus 5, that what I could do here was plug in the 4. And so 2 times 4 minus 5, that was equal to 3. There is something significant about that. Okay? There's something about this function, the way it sits here, and there's a property here that it's got that allows us to be able to do that. So just notice that what happened here is I took the limit as x approached a for some function here, f of x, and I got my limit, and that's fine here. But what was significant in this case was that the limit was equal to f evaluated at a. And we're going to talk about this in another lesson here. What this means, okay, is that our function is continuous. And we're going to explore what that idea means in another lesson here. Now, a lot of the functions you're going to work with are going to be continuous, and so as a result, this is going to be like the standard way to evaluate the limit, would be just to plug in that number and get the value for y. And that's because for most functions that you're going to analyze, as the x approaches some value here, the value that it looks like the function is going to approach, that is actually where it's going. Okay, so where you're pointed is where you're going to get, essentially, is what we have to say by that. So just to kind of wrap up here, this idea of a limit, okay, is kind of a predictive thing. We're approaching, as we allow x to approach a specific value, we're looking to see if the y coordinate approaches a specific value. We have a couple of definitions for that. Both of them are a little meaty mathematically. I did want you to see that because you are going to see those again at a university level. I don't want that to come as a shock or a surprise to anybody when you see that. However, we're not going to make a lot of use out of that. Okay, the epsilon delta notation isn't going to be a big deal for us. In most cases, what we're going to be more concerned with is identifying what's going on with the function as I approach some value from the left, approach it from the right. And as long as those two values are the same, approaching from the left or the right, that's going to be my limit. Again, we're going to talk a little bit more about that in another lesson here too. And in a lot of cases, okay, what's going to happen here is we're going to be working with what we call continuous functions, in which case to evaluate the limit, all I got to do is plug this in. Now, this does not work for all functions, just so you know, because not every function is continuous. However, one of the last remarks that we made a little while ago was that if two functions are almost the same or basically identical at all points except for a group of discrete points, then their limit at a certain value is going to, the limits at all the values there are going to be the same, which means, yeah, maybe it doesn't work for me to plug in my a into this function, but maybe there's a function that's equivalent to this one that I can plug the a into, and that's how I'll evaluate the limit. And again, those are things that we're going to explore later. So there's a lot going on here.